Hey, hello, everybody. Welcome to part 4 of the series, Intro to C. And just like always, I'm just going to wait about a minute or two past the hour here to allow more people to jump in. And then we'll go ahead and kick things off. In the meantime, if you are not in the SANS Offensive Ops Discord server for SANS Workshop, please go ahead and head on over that way so we can have chats or whatever questions about the code or about this part 4 of the series. Everything can be redirected there in the SANS Workshop channel. Other than that, I hope everybody's having a great day so far. All right, we'll give it one more minute and then we'll go ahead and kick things off. All right, so I think that's long enough here. Let's go ahead and fire away with part 4, shall we? So if you still have your code from part 3, awesome. You can look at it as a reference, but we're not going to specifically start from that code base. Okay, so from this particular piece here for part 4, we're going to start over with boilerplate code, looking at the main function here. And if you remember from the registration page for this, kind of the high level topics, what we're going to try and cover today. And it's going to be passing in pointers to functions as parameters, structures, and linked lists, as far as how Windows manages a linked list, how we create a linked list for Windows. Okay. And I envision that we'll be spending a majority of the time for part 4 here on structures and linked lists. So I might not get to dive deep into functions and parameters and annotations and stuff like that, which is completely fine, because I know structures and linked lists can be quite the challenge if it's your first time trying to tackle that kind of concept. So without any further delay, let's go ahead and talk about some structures here. Okay, so in previous parts of this series, we talked about different data types like arrays. Arrays are kind of cool because they can store data of a particular type. Now, the downside to an array is what happens if you want to store different types of data in the same kind of, let's say, structure, for lack of better words, same structure, same kind of data, all right? Data unit, data structure, some kind of container, what have you, okay? You can't do that in an array. It's limited. You can create an array of ints. You can create an array of double words, pointers to double words, a char array, that kind of stuff, okay? Now, a structure, very similar to an array. I use that analogy very loosely, okay? So the benefit of creating a structure is you can have any number of members, okay? So items inside of a structure are called members. So we have structure members. You can mix and match your data type all day long. You can have a structure member that's a char. You can have a pointer to a char. You can have a double word, a pew long, pointer to unsigned long. You can also have structures embedded within structures, embedded within structures. Okay, and Windows internally utilizes structures all over the place, which is why we say that Windows is an object-based operating system, right? So they have a number of these structures that get created to represent some kind of object. And what kind of objects? Stuff like processes, right? Like a process environment block is a structure that can be used to represent a process, okay? So these structures, there are a number of different resources out there that can help you understand some of the structures that exist for Windows. Okay, Virgilius. Virgilius is one such project that has done a pretty awesome job at documenting a lot of these undocumented structures. Okay, what do I mean by undocumented structure? So if you were to go to MSDN and try to find the definition for this structure called PEB, the process environment block, it is not going to give you every single member. Okay, you can see that this is a pretty large structure. Okay, every single process is going to have one of these structures. Okay, the PEB is unique to each process that has been mapped into memory on your system. And the PEB is unique in user space. There are two other structures in kernel space that are used to represent a process. One of those is called the E process. And I'm going to copy and paste this link over here into Discord so y'all have a direct link to the PEB. Hey, let me go back just a little bit. And let's type in E process. Okay, this is the documented definition for the E process structure. You can see it's fairly large as well, being hexadecimal A40. All right, and it has quite the number of members inside of it. We have unions, we have unsigned longs, we also have structures. Let's see, pointers, tons of pointers, all kinds of stuff. Okay, so you can see how inside of a structure you can embed any number of different types inside of it. Okay, there's also other awesome resources for seeing some of the documentation for some of these internal structures that Windows uses. Okay, so I showed you Virgilius. This is the GitHub repo for System Informer, which recently just took in Process Hacker. Okay, they kind of merged together and became one. So let me paste this link into Discord as well. All right. So you have all that, and they pretty much match pretty good with Virgilius. Okay, so you can take a look at those. And then also one other solid resource, if we want to look at some of the undocumented structures here, would be x64 debug. And you can see we have that documentation as well. Okay, so those are my top 3 resources that I go to when I'm trying to understand a structure for Windows that isn't really documented online at MSDN. Okay, so let me go ahead and close those out real quick. Cool. So now that we understand just a little bit of how Windows can use a structure to represent an object, let's go ahead and in our code, let's go ahead and create our own custom structure that we can use internally and learn all the different ways to initialize these structures. Okay, so inside of your main source code file, main.c, you can see on my project here, I have part 4 as an additional project for my solution. And I have one source code file, it's just main.c. I'll explain what the header file is here in just a second when we get to that piece. All right, so if you haven't typed out the boilerplate code for this, please go ahead and do so now. I'll give you just a little bit to go ahead and get caught up. Okay. So how in the world can we create a structure for our program? All right, obviously there are a number of keywords that C reserves and say, hey, if you're going to use this word, it has to be used for a very specific purpose. And one of those words is struct. Okay, so type in a struct, you can see it changes color. Okay, Visual Studio recognizes that as a reserved keyword and says, oh, it looks like you're about to create a structure. Okay, now, before I go any further, one of the things that I love doing when I create my structures is to use another keyword right before struct, and that's typedef. I always create my structures with typedef struct. And the beauty behind this, just my opinion, the beauty behind this is you can eliminate a lot of repetition when you're either creating a structure of a specific type or mallocing something using dynamic memory and casting it to a specific type. Because what you have to do is say struct variable name and casting it from like a malloc or heap alloc to that specific type. But if you do a typedef struct, you eliminate the need to say struct everywhere in code. All right, so what comes next? The piece that comes next after typedef struct is something called the tag, right? It's an internal representation, internal name for the structure. Okay, a lot of times, if you look at various header files for Windows, you'll see this tag start with the underscore, right? So what I'm going to do is I'm going to create this structure to be a Unicode string, right? So the tag, and I'm going to keep it in all caps, Unicode string. And then I open and close my curly braces and end it with a semicolon. Okay, then I go ahead and bring that down on a new line. And depending on your personality and your preference, this can stay there after the tag, or you can bring that curly brace down on a new line as well. Okay, now I'm just going to leave that there. We don't need to have that battle of who likes what. Do you like that curly brace to stay right after the tag, or you bring that down on the new line? Just for readability, for right now, it's staying on the new line. Okay, so we have typedef struct and the name of the tag for our structure. Down here, in between the ending curly brace and the semicolon, this is where we create the actual name that can be used in code for our structure. And what I like to do, I like to keep it the same name as my tag, except I do not include the underscore. Okay, so I have something like that. Now, a lot of times your structures can be dynamically allocated using like malloc or heap alloc or some other function that can dynamically allocate a chunk of memory and return back to you a pointer to that chunk of memory. So what's nice is to go ahead and prepare that with the definition of your structure. So what I'm going to do is adding in a comma right after the name Unicode string, and I'm going to use the asterisk or the splat or the star, and I'm going to say, hey, this is how we create a pointer. All right, so I'm going to prefix this with uppercase P to say pointer, and I will paste in Unicode string. So it's pointer to Unicode string or Punicode string or however you want to say it. We're basically giving the ability to use P Unicode string as a pointer type to this structure later on in code. Okay, let's take a look at exactly how we do that a little bit later. Okay, so now we can go ahead and create some of the members for this structure. Okay, so inside this Unicode string structure, we're going to create 3 members for it. The first one is going to be an unsigned short, or just uShort. Okay, so uShort, and this is going to be the length. And every member inside of the structure must end with a semicolon. Okay, let me repeat that. Every member inside of a structure must end with a semicolon, not a comma. All right, so the length, what is our purpose for this length here? Okay, so for this particular purpose of this Unicode string structure, this is going to be how many bytes the Unicode string is going to hold, okay, without the null terminator. Even if it has one, excuse me, we won't really take an account for it. Okay, so let's add another member here. This is also going to be a uShort. And we're going to call this one the maximum length. And semicolon. Maximum length is going to be the potential number of bytes that this string can occupy before you need to allocate more memory for this particular structure. All right, so max length. And then the third and final member for this Unicode string structure is going to be a pointer to a buffer. So the type for this is going to be a PWSTR. Okay, so PWSTR, and I'm going to keep it lined up with the other members, and I'm going to say buffer. Okay, again, this is going to be the pointer to where the string is located in memory. And if you forget what any of these data types are underneath the hood, go ahead and hit F12. And I'll go ahead and show you that this is a pointer to a wchar. Okay, wchar star. Type def, null terminated, wchar star. All right, that's a winit.h. Cool. Okay, so that's it in a nutshell. That is how you go ahead and you craft your own custom structure. Okay, to recap very quickly, we use typedef struct. Okay, 2 keywords. Typedef is, we've seen typedef before in previous parts of the series. Struct, that keyword is saying, hey, we are going to go ahead and create a structure type, and this is our tag. And I always start my tags with the underscore and your tag name. And then I have the actual name of my structure, comma, star, and P, Unicode string. Then we have 3 members inside of this. Okay. All right. Now that we have created this structure is specific to wchars. Okay, there's another way that you could create another structure that would be specific for, let's say, ASCII or ASCII text. Okay, just in case you don't want to deal with Unicode in your program. Okay, here's how we could go ahead and create another structure that could be a little bit more universal. So check this out. You do typedef struct, and let's just call this one string X. All right, so string X. I'm using X here intentionally because a lot of times in Windows, you will see structures that will have 2 different names. One could be like process info, and process info X could be another one. And the X, the extended, could mean, hey, I've included other members of this structure for more recent versions of the Windows operating system. So maybe, like, for example, Windows XP only has 1 version available to it. Let's just say like process info. The process info X structure is not available for that old of a version. It's only available for, let's just say, Windows 7 Plus or what have you. Okay, so that's sometimes why you might see multiple structures. One's extended because it added new members to it. All right, some kind of update happened. All right, so for this piece, typedef struct string X. Right, so that's my tag. Come down here and create the name here and the pointer. There we go, P string X. Now we'll go ahead and fill out the structure members. I'm just going to copy and paste those. We're going to reuse them. Okay. Now this is where I'm going to make it a little bit more versatile, if you will, depending on whether or not Unicode is defined for this project. So how do we do that? We can use an if-def. So pound if-def Unicode. All right. So if Unicode is defined, then we want to have a PW_str buffer. Okay, again, so if Unicode is defined for the project, this buffer is going to point to a wchar. Else, so pound else, we're going to say just pstr buffer. Then we're done. Okay, so end if. All right, so to recap, using the if-def, we are able to, within this structure, say, hey, if Unicode has been defined for this Visual Studio project, which it is, okay, because this has been grayed out, then we're going to say this buffer is of type PWSTR, pointer to wchar. Otherwise, if we're doing ASCII, then the buffer type is just pointer to char. Okay, so let me show you how to change that real quick. Inside of your project, if you click on project at the top, or project, part 4 properties, or whatever your name is, your project name. Okay, under configuration properties, you have advanced, okay, general and advanced. If you scroll down to character set, it says use Unicode character set. Okay, so I'm going to change this just real quick to use multi-byte. Okay, multi-byte character set, hit apply, hit OK. And we might see that change and boom. Yes, indeed, that changes. Okay, so now Unicode's not defined for this project. ASCII basically is. And now it says, all right, all the buffers for this are going to be pointing to just chars. Okay, let me go ahead and set that back. Just want to show you where you can go ahead and change that option. Cool. So we have two structures that we can start to initialize. So let's go ahead and initialize those inside the function body for main. Okay, I'm just going to create some space here. So how can we go ahead and initialize structures? Well, there are several ways to do this. Okay, one of the first things you have to do every time you're about to create a variable is to tell the type of the variable. Okay, so our type is this type that we just created, right? So string X, for example. So string X, I'm going to copy that and paste that in here, and I'm just going to call it name. Okay, there you go. We've just created a variable of type string X, which is a structure that holds these three members. Okay. At this point in time, those members of this structure have not been initialized. They're going to hold garbage like junk data, whatever happens to be on the stack when main function gets created. Okay. So nothing's initialized whatsoever. Let me show you something that you could do, a very shorthand way to go ahead and initialize every member in the structure to 0. Okay, I'm going to create a brand new variable. Okay, so string X, say name2. And name2 is going to equal, using my curly braces here, inside, say 0. Okay, so every member inside of the name2 structure is going to be initialized to 0. Okay. let me show you yet another way to go ahead and initialize every member to 0. Okay, so let's create name3. All right, follow along with me, name3. We'll leave that there. There is a nice runtime library API to use to go ahead and zero out structures. Okay, and that's RTL secure zero memory. Okay, so go ahead and do RTL secure zero memory, open up your parentheses, and we can see that it takes in a pointer to something as well as a count. Okay, so the pointer to something, that is going to be the address of name3. Okay, so we'll do ampersand name3, right, to satisfy that first argument. So we're passing a pointer to a function. And then next, we need the size t count. Okay, so how do we get that? Well, we can use size of that we talked about in the previous part of the series. So size of, and pass in string x. All right, and then semicolon. So what's nice about this RTL secure zero memory? If you F12 that and see how this is defined, okay, we see we're inside WinNT, line 21,000. Whew, that's a lot of code here. 21,000. We see the two parameters, and then inside the function body, I want you to check this one out. STOSB. STOSB is a compiler intrinsic function, meaning that STOSB is not actually a function call. So you won't see like call STOSB or whatever. You won't see call RTL secure zero memory. You won't see that. Here's why. Force inline. Force inline is saying do away with the call. Because a lot of times the calls add extra overhead for optimization, all that stuff like that. You don't need it. Okay, so this is all forced in line. There is no actual call. There's no prologue set up for this. There's no epilogue, so no stack frame is being built for this function. And STOSB is storing bytes. Okay, we're going to store bytes. Where? This is where. Okay, so wherever this volatile pointer is pointing to, which is that, you pass that in as the first parameter. Okay, so what byte are we storing there? We're storing the byte 0. How many zeros? Well, whatever count is. Okay, so our count was passed in from size of that structure. Let's just go, for example, 16 bytes. So 16 bytes, 16 zeros will go ahead and be stored wherever this is pointing to. Okay. And this is great because in the world of trying to create code that is position independent, like shellcode, stuff like that, using the C programming language, this is a phenomenal API to use because this is optimized away and forced in line. Okay. It's all position independent. And if we really wanted to, you go ahead and eliminate this API call altogether and just use this, right? If you feel so comfortable using compiler intrinsic functions, go for it, right? Cool. Okay, so that's several ways to go about creating structures and how we can initialize some of those, right? So I think it's time to go ahead and do some debugging and see some of this in memory. I'm going to save this program, and I'm going to set up a breakpoint on my line 31, where I'm declaring string X name. I'll go ahead and hit local Windows debugger. And wait and wait and wait. Okay, cool. Breakpoint actually moved on us, moved to the next one down because The first one really isn't being referenced anywhere. It's not being properly initialized, so on and so forth. So skipped it and moved to name 2. All right, in the locals window, we have all of our local variables for the main function. Cool. And we see at this point in time, they are kind of initialized in a sense to just a bunch of CCs. And you can go ahead and expand each one of those and see that each member does have a bunch of CCs in them. And if you go to the watch window is kind of cool. Looks like I forgot to delete some stuff. Any case. One of the things that's really cool inside the watch window is if you type in ERR, comma, HR, it'll go ahead and show you what the last error code was. Okay. For this particular case, as of right now, it's just error success saying the operation completed successfully. But what you can do here is you can go ahead and type in the name of a variable. We already got a few of them in here, but name. Okay, so ampersand name to say the address of name to see where that structure is. I can do ampersand name 2. If I don't have any case sensitivity issues, ampersand name 3. Okay, cool. Now we are effectively watching those variables. Okay. Now here, if you go ahead and step over name 2 being initialized. So name 2 in my window has highlighted all the members red because saying, hey, I want to get your attention. Something changed here. Now we have initialized every member. They went from hex CC to a bunch of nulls. Okay, perfect. That's what we wanted it to do. That's what we told it to do. We said, take all the members that you have in your structure and go ahead and initialize every single one of them to 0. Okay, this is clean. This is what you want to do when you are creating your structures in your program. You want to initialize everything to 0 right away. Okay, always initialize your variables right away as soon as possible. Okay, we can also take a look at the memory window and type in one of these variables as well. So let's look at name 3. So we'll do address of, or ampersand, name 3. So you hit that, and it's a bunch of C's. Okay, cool. Now, if we're watching that memory window, we should see a few of those members change from CCs to nothing but zeros. Let's check it out. Step over, boom, there it is, a bunch of zeros. Okay, so what it did, it took the size of string X, whatever that is, and it says, okay, we're going to shove into name 3, wherever name 3 is, at address ending in FD08 on my system, and we're going to fill in a bunch of 16 zeros. Okay, so cool. Those are a number of ways that we can go ahead and initialize the structure, how you can look at a structure kind of like in memory using the watch window and the memory window. Okay, let's go ahead and go a step further here and play around with creating a few more structures and properly initializing all of these members. Okay, it's one thing to initialize everything securely to all zeros, but let's go ahead and give them the proper values, meaning a legit length, a legit maximum length, and a legit buffer to a string. Okay, let's go ahead and do that. So what I'm going to do is underneath RTL secure 0 memory, I'm going to go ahead and create yet another string X variable. So string underscore X, this is going to be name 4 for me. Name 4, okay. And oops, forgot to do something here. We need to give it a value here, a string value. So P, and I haven't shown you this type yet. So PT str. All All right, I'll explain what this is in just a second. And we'll just, for lack of better words, just say S for string, I guess. And that's going to equal _T, parentheses, semicolon, and then inside the parentheses, I'm going to say hello. All right, what in the world is this nonsense? _T, if we hover, oh, it says it's saying this is a function of type int, which it is not. So that tells me the header file has not been included, which it hasn't. So come up to the top with me, include tchar. Okay, go ahead and include tchar. Then we should be able to come on back down to _T. Hover over that. There it is. Cool. _T. It says it expands to L, then the double quotes and my string hello. The L means this is a wchar. Okay, typically what you'll see is something like that, right? L, double quotes, and then whatever's inside, like your string. Okay, that is a wchar, or we say Unicode. Rather, Unicode's just a standard. Any case, what's so special about this _T? All right, so if I click on that F12, okay, you can see how this is defined. Okay, and then you see this one here, F12 that. All right, this craziness. Okay, basically, what this is being used for is to, on the fly, it'll change the type of your string. It can change it back and forth from wchar to char. And that's why I use the ptstr. Okay, so ptstr, if you F12 this, it says, oh, this is a lpwstr, so a long pointer to wchar. Okay, that's what that is. Okay, now let me show you how this changes. All right, it knows right now that our project has defined Unicode because in the project settings, our character set is Unicode. All right, now remember, I want you to take a look at this, and also on your side too. The _T expands to L and then your string. So let's switch it up real quick. Go to project, properties, character set, change it away from Unicode to a multibyte. All right, we'll let that switch happen. And now look what _T expands to. It expands to just the regular char string, hello. And if you hover over the PSTR, we see that the W is now gone. Okay, it's no longer LPWSTR, it's just LPSTR. Okay, how is this beneficial at all when you're making like a Windows program? Okay, one of the things that it gives you is the flexibility for somebody else to go ahead and use your code and change the support for Unicode. Maybe they don't want Unicode to be in the program for whatever reason. I don't know why. Everything just has to be ASCII, so they go ahead and they undefine Unicode, and everything is just straight up ASCII. Okay, this will automatically change to that, and everything should be fine that way. Okay. Cool. So all of that just to create this one variable, S. Okay. Now, inside of our name4, right, here's another way to go ahead and initialize members. All right, equals our curly braces. Inside the curly braces, what you can do is you can use dot notation to go ahead and start to specifically hit members of the structure. Okay, so we have length, max length, and buffer. Cool, so let's go ahead and you can do any order you want. So I'm gonna start with the last one. Dot, look at that, IntelliSense popping up already. Let me pick out the members of this structure. So I'm gonna say dot buffer equals S. Okay, so when this compiles and when we run this, dot buffer will be initialized to S, okay, wherever S happens to be pointing. And then let's go ahead and hit the other. let's do max length. So maximum length equals, what does this equal? This is going to be the total size of this string before we need to maybe allocate some more space for it. Okay, so we're going to use size of for this. So size of S. So that takes care of maximum length. Now let's go ahead and tackle the length piece of it. So dot length equals, and this, all right, so this is interesting. If you've ever tried to get like the size of an array, stuff like that, you might see some math being used with size of. Okay, so something like this you may have seen before depending on your previous exposure to C. So size of S minus size of, so size of here, and then in parentheses again, I'm going to say S because I'm going to use indexing and list indexing here and go to the very first member, 0, index 0. So indexing item 0 for whatever S happens to be pointing to. Okay, so what's going to happen here is going to do a little bit of math to find out what the exact length is for this particular value. Okay, sometimes you'll see different sizes or different values here. Okay, so a different value here, this could be a lot larger than this value here. Okay, so basically we're just taking the entire size of this hello minus size of S at index 0. So it's come into this guy right there, that H. Okay, that's kind of what we're looking at right there. This is another way of using dot notation inside of the curly braces to initialize the members of your choosing for a structure. Again, it's pretty cool because you can just hit any member in any order that you would like to hit. It's just a lot of unnecessary code to type. I'll show you another way to make this a little bit easier to do. Okay, so that is how you can be specific. Now, let me show you another way to do this. It's like, oh, goodness, Jonathan, how many different ways are there? It was like an infinite number. Kidding, there's really not an infinite number of ways, but there's tons. I just showed you a way to hit this specifically. So now I'm going to show you a way that we can initialize some of the members of the structure by order of how they are defined. Okay, what in the world do I mean by that? Well, string X has 3 members, right? So what I can do is put in some placeholders, if you will. All right, so right here, the first item is going to be for the first member of the structure. This spot right here is for the second member of the structure. And then this one is going to be for the third member of the structure, or just the last member of the structure. Okay, hopefully that makes sense, right? It's all in order from first member all the way on up to the last member of the structure. So what we'll do is, and let me make sure I'm initializing this correctly, length, okay? So I'll just go ahead and copy this. So I'll put that there for the first item. I'll move to the second item, or the second member of the structure, which is maximum length. That's just size of S. And then the last piece here is just the buffer, okay, which is just be S. Okay, cool. Now I'm going to go ahead and I'm going to save this, and I'm going to move my breakpoint to name 4. Okay, now I'm going to go ahead and hit local Windows debugger. Wait for it to compile down. Away we go. Okay, cool. And in my watch window already has the address of name 4, the address of name 5. All right, so please go ahead and add that to your watch window, address of name 4, address of name 5. And also, if you would like, you can go ahead and put that in a memory window if you want to. Okay. So we hit our breakpoint at name 4. We'll go ahead and step over that. Boom, we see that is all changed to red. And I'm going to expand that down. It says length is 7, max length is 8. And then our buffer is hello. The buffer is the pointer to the string hello. And let's look at the initialization for name 5. It should be the exact same thing. Go ahead and expand name 5. It's all CCs. Let's get rid of those. Boom. Exact same thing as name 4. Length 7, maximum length 8, and buffer is hello. And in the memory window, you can also see how this has changed. We see the bytes are now in red for something that has been updated. And I want to draw your attention to something that was not updated. These CCs right here. We have 4 bytes of CCs in between the structure members that we created. All right, so think for a minute, think for yourself for a minute. Why in the world might that be the case? Why do we have some junk, some garbage in between some members of this structure? Okay, so while you're thinking about that, let me explain how this is laid out in memory. We have our first structure member, which is the U short, right? U short length. And then the next structure member, which was a U short for maximum length. And then we had our pointer to our buffer. Our pointer is an 8-byte pointer, right? So 64-bit pointer sizes are 8 bytes. 32-bit, they're 4 bytes. And the U shorts, we can see here, they're 2 bytes, 2, 2, and 8. So 2, 2, 8. 2, 4, plus 8. And then this stuff in between. Okay, so if you're ever trying to figure out like what the size of a structure is in your head, just by looking at the members of it, okay, be like, all right, 2 bytes plus 2 bytes, I got 4 bytes, plus an 8-byte sized pointer. Okay, cool. But what happens is this. The compiler went ahead and padded out our structure. It gave it an extra 4 bytes, all right, to make everything aligned nice on byte boundaries, so on and so forth, which in this case, who cares? It doesn't matter that padding was added in here. It's whatever. Now, in the realm of trying to maybe create a structure that would be specific for sending messages back and forth from your implant to your C2 server, you might care about this padding, this junk. Okay, so not going to cover it in depth here, but there's a way to change this. And that is using a preprocessor directive called pragma pack. Pragma pack, and then it'll say, okay, what do you want? How do you want to pack this down? So let me go ahead and just stop this for a second. Let me stop this debugger. We saw what we need to see in memory. Come on back up here to our structure. Pragma pack, in parentheses, 1. Pragma pack 1. What you're telling the preprocessor is going through the code, it's going to see that and be like, ooh, I have a new directive. Okay, what do I do? What do I do? Okay, I need to make sure everything in this structure is packed on a single byte boundary, meaning I cannot pad this out. So in between here, in between max length and buffer, I can't add extra stuff into it. Everything is going to be right next to each other in memory. Okay. Now, again, this is only really useful when you're trying to send something back and forth over a socket or whatever for C2 communications. Maybe the structure that you made has the command given, the command results, something like that. Okay. That's where that really comes into play, in my opinion. And Raymond Chen, he has a blog post about this. Okay. So I'm going to go ahead and drop this link in Discord. Hey, Raymond Chen, awesome guy. Has amazing blog posts, the old new thing. All right, what does Pragma Pack 0 do? Let's see. Let's go to MSDN. Pragma Pack. All right. So I'm trying to see what the requirements are, because I believe 0 is not an option. Specified values and bytes used for packing. Valid values are 1, 2, 4, 8, 16. Okay, so it's definitely multiples of like 2 here or whatever. Okay, so sorry, TPZ, 0 is not a legit option. All right, 1, 2, 4, 8, or 16. Yeah, sorry. Honestly, it doesn't really make a whole lot of sense to do a Pragma Pack 0 anyway, right? Because in my mind, a 0 would be the same thing as 1, packing everything on byte boundaries. Okay. Yeah. Yep. Indeed. Okay. Oh, cool. They even give documentation or examples in MSDN documentation of using Pragma Pack. And how the padding can change. That's kind of cool. So yeah, if you want to play around with that, look at MSDN documentation for Pragma Pack. Cool. All right. Let's go ahead and move on a bit more, shall we? I know we're spending a lot of time here on structs, but I want to make sure these are covered in depth. So name 4 structures, name 4, name 5. It is very annoying to have to do size of the variable, size of that, and the first index of that variable, right? That's annoying. There is a much better way to go ahead and do this by way of creating a macro. All right, so the macro we're going to create it's already made out there in the Windows world, but we're going to make a little twist. Okay, we're going to create a twist for this. And the twist is we're going to give it the flexibility to support Unicode or ASCII, or wide characters or ASCII characters. So what I'm going to do, and what I want you all to do as well, is right underneath the pound define cdecal, we're going to create a new pound define. Pound define RTL constant string A, and then in parentheses S. I want you to copy and paste that again and change the A to W. So what we're doing is we're creating 2 macros. One macro to deal with ASCII and another macro to deal with WCHARs. Hey, no worries. Yep, glad you could join. Better late than never, I say. All right, so we have RTL constant string A and RTL constant string W. Now, what are these going to do? These are going to initialize the 3 members of the structure. So here's what we do. Size of, right? So remember, the first item of that structure is the length. Okay, so size of S minus size of S and the first index. Okay, so that takes care of the first one. The next member is going to be the maximum length. So that is just size of S. And then this piece. Okay, so pay attention to this piece. This is where we're trying to initialize the buffer for the structure. Okay, so we know we're going to be passing in the pointer to a string, but what type is that string? Because this is going to be RTL constant string A, what's coming in through here has to be typecast to ASCII. So we'll do S here, but we're going to do a typecast of PSTR. Okay, pointer to char. And now down below here, you can just go ahead and copy paste that definition of that macro there and change this though to be W. Okay, PWSTR. I like my curly braces to align a little bit nicely there. Okay, cool. So we just created two macros. One macro to handle ASCII strings or ASCII characters, another to handle wide. Now, one thing that you can do to make it a lot easier for people to use these macros is to create just one word to handle both of these. So what do I mean by that? All right, we first need to check if Unicode is defined. Okay, I'm just going to say else and if. I'm just going to type it out so I don't forget. So if Unicode is defined, I want this definition to exist. And that is going to be RTL constant string. Oops. And this is going to be is the W version of this. Okay, cool. I'm going to copy and paste that line, come down here to the else. And of course, we're going to change that to A. So what we're doing here at this point is saying we are creating a custom definition of RTL constant string. And depending on how Unicode is defined for the project, it's either going to expand as RTL constant string A or RTL constant string W. Okay, so let's see how we use this, this newly created macro here in our code. All right, so keep on going down into your main function here, and let's create yet another string X variable. So name 6 at this point. Okay, so here what we can do is use our RTL constant string macro to initialize all members of this structure. All right, RTL constant string and the parentheses. And then because we're just using RTL constant string, you can flip-flop to A or W. What's inside needs to be able to flip-flop as well. So we're going to use underscore T. You could just use S if you wanted to. I'm going to change it up. Hey. Cool. All right, I'm just going to separate that just a little bit. All right, so hovering over our macro says, hey, this expands to RTL constant string A because Unicode has not been defined, it's not being supported for this project. Okay, cool. Now I'm going to go ahead and change my breakpoint to name 6 and run it. Sweet. In my memory window, I'm going to say address of name 6. There we are. Go ahead and step over this. Name 6. Boom. Go ahead and see that has been updated. Okay. Cool. Now, one thing of interest. Remember, I did not remove the Pragma Pack 1, that's still there. So look at this. Inside of the memory window here, everything is all shoved right next to each other on byte boundaries. Okay, let me show you in a different memory window. Address of name 5. Oops, sorry. It's going to be the same for every single one. All right. I thought I had one that was Unicode string where I didn't Pragma pack it. Any case, if I initialized one that was for Unicode string, you would see that padding again, right? You would see the 4 bytes of hex CCs after this one. Okay, so we'd see CC, 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 then the address for buffer, right? Cool. So that's how Pragma Pack looks, or that's the effect of Pragma Pack 1 in memory. Everything gets packed right next to each other on byte boundaries. Yeah, undo on that one. Cool. Okay. All right, let me go ahead and stop that. Recap just quickly here. We looked at how we can create structures. All right, one is specific to Unicode strings, and this one is a little bit more versatile. Okay, this isn't perfect by any means. Okay, a lot of it still can be enhanced upon. But with the string X, saying I don't care if it's Unicode or ASCII because my members can flip on the fly. Okay, so that's kind of cool. And then we explored a number of different ways to go ahead and initialize members of the structure, saying all members initialize a 0, same thing here. And then coming in with dot notation to go ahead and hit each single structure member. And then by order of definition. So saying, hey, the very first member, we'll initialize that. Second member, okay, for the second place. And then third place, the last member. And you can do this with any window structure that's currently supported, any structure that you create on the fly that might be custom for your program. Okay, next, let's talk about how we can pass structures to functions by way of pointers. Okay, so back to the top, and it would be proper at this point in time to create a header file where all the structures are defined and all functions are prototyped in a proper header file. But I don't care right now to go ahead and do that. All right, so after all of these definitions of the structures, I'll create a prototype for one of our functions here. So void return type, calling conventions WinAPI, standard call. And the name of the function is going to be dump struct. Okay, so dumping a structure. And we're going to go ahead and we are going to accept one and only one parameter. And this is where I want to talk about Sal annotations. Cool, let me save that. Okay, Sal annotations. If you have taken my course 670, you will know already about Sal annotations and my opinion of them. So Sal annotations, what in the world are they? What are they used for? I love them. And if I do code review for you and you don't have them, I'm not going to be a happy camper because in my opinion, they really enhance readability of the code. And also, I think it's kind of obvious what your function is going to do with the parameters coming into it. Okay, let's explore that. This Sal annotation right here, by the way, Sal structured annotation language. No, don't worry, it's not another language like a programming language that you have to learn. It's a way to annotate parameters of functions. You can also annotate functions themselves using Sal, and you can annotate members and structures as well. Okay. What's so lame there, TPZ? So for this piece right here, in what in the world is the in annotation? In means that the function should be treating the data coming into it as read only, and it is required, meaning I should not be allowed to pass in a null pointer, all right, for the process name. That should be caught. When I go to compile this down, it should highlight it and it should give me like a little green squiggly and say, hey, silly, you cannot do that. Based on the requirements or whatever for dump structure, you cannot pass in a null parameter here. It's required, and it's going to be read only. Okay, where are some good resources to go ahead and learn SAL annotations deeper? Well, there's a header file. You F12 that, it should open up sal.h. And the in parameter here, it says in annotations are for parameters where data is passed into the function but not modified. Okay, hence read only. Okay. Okay. It also says in can be used with non-pointer types. Okay, so it doesn't matter if you're passing a pointer to something or if it's just like a regular int, you can still use in, right? But it says although it's redundant. Okay, so feel free in your own time. You can go around and read the rest of sal.h. Everything is categorized, if you will. So we have in outs, stuff to deal with buffers. Okay, so like in reads up to size bytes, out parameters. Okay, so there's also another solid resource for learning SAL annotations. Obviously, you have MSDN. MSDN documentation for SAL. Not another programming language. Yeah. And also you have this blog post on Code Project. Code Project for SAL version 2 annotations. Okay, those are awesome resources. All right. And oh, by the way, Windows uses SAL annotations for every single function that they create and pass out to you in your header files. Okay, I'll show you a few here in a second. All right, so back to dump structure. Dump structure, we have our in parameter, and we're saying the in parameter is a pointer to process name. And because we know it's required, you don't have to check for a null pointer in the code. One other thing that's kind of cool, if you do 3 forward slashes, I'll go ahead and pop open like a little summary for how this API can be used. You can say blah, blah, blah. All right, create some other summary of how dump structure is used. And then parameter name. It already pulls a parameter name, and it's a process name. We're going to say pointer to string X object. Returns void. Okay, I'll save that off. And now what we need to do is we need to actually create the definition for this API. I'm going to do it at the very bottom here. And because we used SAL annotations before, I don't want to specify them again. It wouldn't be too bad though, since this one only has a single parameter. But if you have a function like create process or what have you that has like 8, 9, 10, maybe more than that arguments, you don't have to keep doing annotations over and over and over again. So what you can do is right before the return type, you go ahead and type in use decal annotations. And what that is going to do is it'll go to where this API has been prototyped, and it'll go ahead and say, all right, all the annotations that dump struct has, I will apply them to all the parameters down below. Okay. The difference between SAL version 1 and version 2 is basically just syntax for how it works. I believe sometimes what you will see is something like this, something like that. like that. And then it's like really old school. You see that? Okay, so a lot of times if you're looking at code on GitHub, you can see like how well they know SAL annotations by what version they're using. A lot of times, a lot of people just copy paste blindly other code. And if they do that, you might see old school SAL annotations instead of upgrading to SAL version 2. In any case, I mentioned that because we have an in annotation for this parameter, you don't have to check for null pointer because it's not going to be allowed. So I'm going to go ahead and just skip that. Okay. Now, in order to process this, one of the things that you can do is you could use printf, wprintf, or what have you. There's also printf types that will go ahead and change based on Unicode being defined or not. But we're just go ahead and skip that. And I'm going to say printf and right here, HZ, I think it's HZ for ASCII, because I think WZ is for Unicode. What's cool about the Z format string specifier is it understands a specific structure, like a Unicode string structure or the string X structure that we made. So all we have to do is, no, not PABC. What in the world was that? It's process name. Okay. That's all we should have to do because it's going to know this structure as ASCII, and it'll go ahead and access the buffer member of the structure and print that out. So let's test it. Let's test this out here. Dump struct and address of name 6 and semicolon. All right, save it. And I'm going to get rid of that breakpoint and just go ahead and run it. See what happens. Exception thrown. Oh no, yeah. What we got? We got nothing here. Oh, fun. All right, so crush that. And inside of our dump struct. Okay, yep. Go ahead and stop. Okay, so we had an exception here inside of printf. Okay, so what we can do here, just to play around with Unicode, I just want to see if this changes anything. I'm going to switch it. I'm going to switch my project properties to Unicode. Okay. And I really don't care about Pragma Pack 1. It's not necessary for this whatsoever. Okay. Definitely don't need it. Again, it's really only useful for C2 comps and stuff. Okay, so this dump structure here, let's go back down to that. In parameter, p string x, process name. Okay, cool. And we're calling dump struct for address of name 6, which is how we pass in a pointer to something, a pointer to the structure type p string x. Okay, and then inside of our dump struct, go ahead and scroll down here. Let's change this to W. All right, so WZ, HZ, I thought for sure HZ is for ASCII. I'm pretty sure WZ is for wide. Okay, but let's go ahead and play around here. I'm going to hover over T to make sure. Interesting. There it is. Okay. Yep. Okay. So cool. Everything took effect. Now Unicode's defined. So we got PWSTR buffer. Cool. And let's see what happens. YOLO. Access violation again. Let's see. Nope, we're all good to go. Yeah, I don't feel like diving into that exception. Maybe it has something to do with that format specifier. Like I said, I thought H was legit. Oh, so HZ does work, but without Pragmapack. Thank you so much for that, Julie. Appreciate that. So I was kind of right. It is HZ is a legit format specifier, but for whatever reason, it doesn't like Pragmapack. And I think that's because of that Z operator. I think the Z can't use Pragmapack because it's expecting it at a certain place. That would be my assumption. WZ doesn't like Pragmapack either. Yeah, interesting. Okay, I'm going to go with that working theory that is expecting it to not be on byte boundaries. It has to be padded out. Yep. Cool. Thank you for that. Really? It worked fine for you with Pragmapack. Interesting. There's no way. Screenshots or it didn't happen. Screenshots or it didn't happen. I'm with Julie on this one. It doesn't like the Pragmapack because it didn't like Pragmapack for me. Any case, that's definitely some weird behavior. All right, so that's how we can create structures, create pointers to structures, which we'll dive more into here in just a second. Passing a pointer to a structure, to a function, and just touching base on SAL annotations. I do want to show you real quick, dump struct, null. Okay, so null, because this is C, null does not expand to 0. Null expands to void star 0. Okay, that's how we create a null pointer in C. I'm going to save this. What's that window? Bye. Okay. And I'm going to compile this. Now, if you'll notice, nothing is highlighted yet. Okay, so let me just compile this or build it. Control B. There we go. Sweet. So if you look at the error list or the warning, it says for main.c line 67, parameter 1 could be 0. This does not adhere to the specification for the function dump struct. Well, how does it know that? How does it know it doesn't adhere to the specification? Because we created that. We created that specification for dump struct. We said in. In means required. It has to be there. It has to be a valid pointer. Okay. So when we pass in null here and we compile and we get that green squiggly. And if you hover over dump struct, it says, we can see the summary of dump struct, blah, blah, blah. Process name, pointer to string X object returns void. Okay, that's the summary and whatever that you made as a comment about the prototype. All right, it's kind of cool to see that stuff. Okay, and down there also says compiler warning 6387, the whole thing. Okay. Shouldn't that be an error instead of a warning? You could do like W4 to treat all warnings as errors. But it's going to be like, hey, if you really want to go ahead and do this and pass in null, something that could be 0, right? What does it say? Could be 0. Not that it is 0, saying it could be 0. So for example, let's say I allocate something on a heap using like heap alloc. Heap alloc is not guaranteed to succeed. So if that pointer doesn't actually point to that chunk of memory, it could be null. It could be. And if you go ahead and just blindly pass that in to like dump struct and be like, hey, this could be null. You haven't checked for it before you pass it. So that's why I think that's kind of why it's saying it could be 0. It doesn't adhere to the specification here. right? I think that's why it's only saying warning. All right, but of course it could say treat all warnings as an error. Okay. One note, real quick, since the thought just popped into my head, dealing with passing pointers as arguments to functions. A lot of times you'll see and hear people experienced and new to C saying this is the same thing as passing by reference. Nope, it is not. C is limited to the fact that it has to pass by value. Even if you're giving it the pointer to something, okay? Because guess what? The value that's being passed in is a pointer. It's a memory address. That's the value. C is strictly limited to passing by value, even if you're using pointers. You cannot, I repeat, you cannot in C do pass by reference. Okay, that is a C++ ism. C++ has such things as references to objects and references to variables. Okay, so in C++, I can go ahead and do something like this. You could do ampersand. Okay, right? You wouldn't need that at that point. All right, and it's yelling at me because it's like, I don't know what the heck this is. That's the C++ thing. That's how you can say, I want the reference of process name. Okay. If I ever decide to do a intro series to C++, we'll dive into that. All right. So in any case, back to name 6. Okay. So moving forward to linked lists. Okay. Let me scroll down a little bit more. There we go. Linked lists. All right. So structures, I think we beat that to death, right? Linked lists. What in the world are they? What are they used for? How can they benefit you as a programmer for Windows applications, and more specifically, you as an implant developer for Windows? All right. So Windows uses linked lists everywhere. Okay. I gave links to Virgilius and stuff like that. Let me go ahead and open up again. Virgilius, Explorer kernels. It's Tim, just clicking. Who cares about the version? Beb. All right. Windows will maintain a linked list of PEBs. Okay, and also within the PEB, there will be a linked list of, we'll say, all the modules that have been mapped into memory for this particular process. Okay, so the structure type here, PEB loader data. If I click on that, this structure has 3 items that are of type list entry. Okay, what in the world is list entry? List entry is yet another structure. So we see now we're 3 layers deep of structures within a structure within a structure. So if you look at list entry, we see yet another nested structure of list entry called flink and blink. Okay, so these are pointers. See the star here. All right, so list entry star flink. And the very next item is blink. All right. This is what is called a forward link. Blink is the backward link. Windows will go ahead and create what they call a circular doubly linked list. Okay, that's a mouthful. Circular doubly linked list. Why do they use that language? Does that verbiage mean anything? Well, absolutely it does. A linked list can be single or double. Single means this item right here, the blink, is gone. Okay, that does not exist. A linked list becomes double when you have a backwards pointer. Okay, a circular doubly linked list means that at the very, very beginning of a list, a lot of times that is referred to as the head of a list, or some people see the list head. That is where you have just a list entry structure way off the middle of nowhere in heap land, and it only has a flink and a blink. That's it. Nothing else. These two entries are basically just initialized to wherever this happens to be allocated in memory. That'll make sense when we look at it in code. Then what you can do is you can add another item to this, okay? And then this flink will be updated to point to that item. Okay, let me go back to the code. I'm going to draw something out. List entry. All right, remember that's a structure. List entry. I think that's enough. There we go. There we go. Okay, so let's say just for giggles, right? This is a process info structure that has a proc name, then it has a PID. Down here, it has the base address. And it's the exact same thing over here. Okay, so process info structure. And name, PID, base address, so on and so forth. Okay. This list entry item can be located anywhere you want when you define your structure. It doesn't have to be at the beginning, doesn't have to be at the end, can be in the middle. You can have multiple of them, like Windows uses internally. There are a lot of times they have multiple list entry items all throughout the definition of a structure. Okay, what's happening here is when this gets allocated into memory, okay, so let's say this structure, this process info structure type, it gets allocated to memory using something like heap alloc. Okay, boom, it's a chunk of memory. And then you create another one. Okay, boom, another process gets created. You want to capture that. You want to capture the name, the PID, the base address at a minimum. So you allocate another chunk of memory for that. They're not linked yet. They're not linked. They're just separate in the heap world. In order to link then, you would have to come in and access the list entry. And remember, this is a structure. So come in and access the list entry dot flink. And so list entry dot flink is going to point to this guy right here, which would be the list entry. Okay. And then over here, let's say right here is the head list. I'll just say head L because running low on space here. Should have moved everything to the right a little bit more. Shame on me. Right there. And the head list only has a list entry type. That's it. And it points to that. Okay. So in a Windows world, in a circular doubly linked list, all these list entry items only point to other list entry items and so on and so forth, other list entry items. Now, the very, very last entry, the very, very last item, the list entry flink is going to point back to the head list. Okay, so that's kind of how we start getting that circle, if you will. Okay, and the list entry blink, the backwards link, as you expect, just goes back. Just goes back. Okay, just back. Okay, everything is a circle. So when you're doing an iteration over a doubly linked list, how in the world can you determine if you're at the end of all the entries? How can you tell if you have completely iterated over every entry? Well, the first thing you need is you need a pointer to the head of the list. Okay. Then at the head list to access the very first entry, you say headlist.flink. Boom. I get to right here. This is the first legit item of a doubly linked list. And then we go ahead and we advance to the flink. Whoop, you come over here. And then to tell each iteration that you do in your loop, you're making sure that your current item, so let's say we're here. Let's say we're right here looking at this structure in memory. If this item's list entry flink equals head, all right, you know you're done, right? It's done, because what's the process after that? Because you're back at the beginning. You're at the beginning of the circle. Okay. Hopefully that makes sense, right? Looking at some crazy picture art. Hopefully that's a way to kind of visualize what this can look like. But let's go ahead and code this up. All right, we're gonna make a new structure. All right, we're gonna create the process info structure. Okay, so the process info structure, we'll say type def struct underscore process. Let me move my cursor. Info. I'm just gonna say X. We'll pretend that this is the extended version. Okay, so fill out the tag, and I come down here, the name, and get the pointer. Okay, so P process info X. And inside of this, I would like this to have the process ID. Okay, process ID. A lot of times APIs will return back to you a double word, which is fine. So double word. Process ID semicolon, and let's go ahead and add the list entry item here. We'll say this is the second member of the structure will be list entry, and we'll call this one process info links. Okay, so this is how we're going to link. This is the member of the structure to link everything together. And inside of this, we need to have the name, the process name. So I'm going to use the structure Unicode string. Unicode string. Could do process name. Let's just do name. Okay, that's good enough. It's a process info structure, so name kind of is like, okay, you should know what the name is. And then let's add H module. And this is going to be the image. Oh, what's that field called in the PEB? Image base address, I think, is what it's called in the PEB. Okay, so image base address is where an image would like to be loaded in memory. The system loader doesn't care about your preferred image base address. It's got its own place in mind. Okay, so that's where your MZ should start. And then let's add another one. All right, handle to the current thread. And semicolon. Oop. All right, cool. So we have a number of items in here, all multiple different types. So this would be fun to initialize here. Cool. Let me save that one. And coming down here inside of main, I go ahead and add some more space here underneath the dump struct. I'm actually going to comment out dump struct, all right, because that's not relevant right now for this piece. Okay, so for linked lists, I like to use dynamically allocated memory. Okay, Windows does it too, so should you. We're going to create a couple of variables for all this linked list stuff. First one is a Boolean type of variable. I'm going to call this one is empty. So B is empty. Set that one to false. I'm going to use this variable to be an indicator if the list, if the doubly linked list is empty, or if it has something in it that I might need to process. So the next thing is I'm going to create a pointer to a list entry, and I'm going to call this the temp, the head list. All right, so temporary head list. Initialize that to null. I'm going to create another plist entry, so a pointer to a list entry. This was just going to be temp. Initialize this one to null. Okay, the reason I'm creating this one is it's useful when you're doing like a while loop or something. Okay, it's just basically a temporary item for whatever you are iterating over at that moment in time in your loop. And then we need to have our process info x struct. All right, process info x. I'm going to say just proc info equals null. Okay, so everything's been initialized. Sweet. All right, now what we need to do is we need to actually initialize this list. So we initialize that by using our temp head list to say this is going to be the head of the list. All right, so temp head list equals, and this is where we're going to call our Win32 API called heap alloc. Heap alloc is going to dynamically allocate a chunk of memory in heap space for this process, and we need to cast it. We need to cast the return type to be of type plist entry. So plist entry, and now we can make our API call, heap alloc. All right, so heap alloc needs a handle to the heap, and a handle to the heap is, we're going to solve that one using the API call get process heap. Okay, so get process heap, you specify that without any arguments. Now heap alloc needs some flags. Okay, you could check out MSDN documentation to see some of the other options for flags, but of interest to us would be to allocate this chunk of memory and have everything initialized to 0. So the flag we're going to use for that is called heap 0 memory. Okay, so heap 0 memory. And then what's the chunk size that we would like it to allocate for us? So this chunk size is going to be the size of our temporary head list, which is just a list entry item. Okay. Now don't do size of p list entry, because that's going to be the size of a pointer. That's not what you want. You want the actual structure, right? So size of list entry. Okay, so this is our way of getting the very first item initialized, ready for our doubly linked list. Now, whenever you allocate a chunk of memory, you better error check that. Okay, I know I've seen tons of code where people will call it malloc or something, and they just go on. Like, malloc never fails. It always allocates memory until it doesn't. All right, so we're using DW status to keep track of our error codes. So we want to get the last error. All right, so get last error. A lot of Win32 APIs will go ahead and set this error. They'll say, whoops, we failed for whatever reason. Like heap alloc failed because we couldn't allocate some memory. So it's going to set that last error so we can get the last error and we can print that out. So printf, we'll say heap alloc failed with error percent. Oops. I think LU. I think LU is for unsigned long, which is double word, and DW status. And that's what we want to return. Okay, cool. So we allocate a chunk of memory, we error check it, and if it fails, we bail. Okay, done. Now, if we're good to go, now we can go ahead and start to truly initialize the head of the list. How in the world do we do that? Now comes time to look at this header file that I made. Okay, initialize list head. This is a legit Windows API, but it's only available in the kernel because it's defined in the WDM, I think, the WDM.h header file, right? So it's like Windows drivers. I think there's another header file like NTIFS or NTDDK has it as well. So all I did is I plucked out these functions and brought them in here and deleted some other things that are specific for drivers. All right, so now it's user mode friendly. All right, here's what's happening. If you want to type this out, please do so while I'm explaining this, this API. Okay, so forced inline. I talked about forced inline already. It's going to be optimized away, and you're not actually going to see call initialize list head. Void, return type, nothing, all right, void. And then we have our one and only parameter, which is an out parameter, saying, hey, you need to pass me something. It's required. It's required to give me a pointer to the list head, and it has to be writable because it's out. So I'm going to write to it. I'm going to write to that pointer. What in the world are we going to write to it? How are we modifying this pointer? Okay, so we come in and we access the Flink member of the list head structure. And that is going to equal Blink. And that's going to equal list head. Okay, so Flink and Blink are going to have the same value at this moment in time. And that's list head. I personally despise when people do multiple definitions and initializations on the same line. It can be a little bit confusing. All right, to enhance readability, I probably would have broken this up on a couple of lines. In any case, Flink and Blink will be initialized to the same value, and that is list head. And then we just return. That's it. Okay, so let's go ahead and let's initialize the head list. Initialize. Oh, yeah, we got to include it. Include list helpers. All right. By the way, if you have not been able to create that header file, here's how you do it. So one of the things you can do is under the smart folders here, smart folder for header file, right click, add, new item. Add new item, header file, create the name as you see fit. Then you can add it to your project. Tell you what I can do. I can paste that. Let's see, let me paste that in here. All right, it is in Discord, initialize list head. You should be able to copy and paste that over. Okay, at the end, I will drop the entire header file. Now we should be able to call initialize list head. Yep, there it is. Okay. Give the name of your variable, temp head list, and semicolon. Okay. So here, what I'm going to do is save this. Just want to build it, want to compile it, see if it's legit so far. Okay, build one succeeded. Awesome. And I'm going to set a breakpoint on this call to initialize list head. And local Windows debugger. You go ahead and get rid of some of these. We don't need those anymore. All right, so I'm watching the address of temp head list, and I'm going to say that over here as well. Temp head list. Okay. So temp head list, we have successful allocation of a chunk of memory. Cool. Now initialize list head. I'm going to expand this out, expand that one out here, and we see Flink and Blink. We should see those two members change here. Okay, and this should be the exact same values, exact same addresses. So step over that one, and boom, there it is. Okay, ending in 38D0. The Flink as well, 38D0, and the Blink as well is 38D0. Okay, so at this moment in time, it's just pointing to itself. Okay, that's it. It's like giving a hug to itself, a self hug. Okay, that's all it's doing. Nothing else has happened yet. We haven't added an item or anything else like that. Cool. Go ahead and stop that. Okay. One of the things that you might want to do is you can use an API to check if the list is empty. Okay, so let me go ahead and copy this and put that into Discord here. Okay, so here's how we check if the list is empty. We have a required parameter to a pointer to a list entry, which is the head of the list. Access that Flink. Does that Flink equal to list head? Yeah, it does. If it does, then go ahead and return non-zero to say the list is empty. If it is not empty, meaning it has a valid item in it, return 0. Okay, or false. So let's go ahead and call this one. Is list empty? Whoa, what was that? I don't know what that other crazy thing is. Okay, so is list empty, and passing it temp head list. Okay, cool. Let me compile that. Let's just see if we get any crazy warnings. Don't care about that one. Ah, what's this? All right. B is empty, holds a value that must be examined. How does it know that must be examined? Okay, let me F12 that. Look at this. Another style annotation. It says must inspect the result, meaning if you store the result of this API in a variable, I want you to check out that result. Did it fail? Did it succeed? Something. You got to check it. That's why it's highlighting this too. It says the exact same warning. It holds a value that must be examined. Well, I don't care. All right, we're gonna proceed on anyway. So local debugger. Initialize list head. Step right over. And step right over this one. Just want to see what we get. Okay, so B is empty, returns non-zero, meaning it is empty. Of course it is, right? It's empty because the list head, the Flink and Blink point to itself, basically. Okay, it's that self-hug. All right, let me go ahead and stop this. All right, so we have initialize list head and is list empty. Now what we need to do is we need to go ahead and add something to the end of the list. That's going to be this guy right here. Insert tail list. All right, insert tail list is in Discord. Okay, so what's happening here? We have two parameters that are in out, so they're annotated as in out, meaning they're going to be read to or read from and written to. Okay. So it's going to read in the value of list head, and we're going to modify something here for list head. And then the other in out is the current entry. Okay. The entry that you want to add to the end of the list, the tail. Okay. The end of it. So right here, we have like a temporary placeholder, if you will, called blink of type list entry pointer. All right. Pointer to list entry. And blink is going to say, all right, list head, I'm going to look back. So look backwards and grab that pointer. I'm going to take that. I'm going to store that for just a minute. Then we're going to go ahead and look at the current entry. The current entry that you wish to add to the tail of the list. And we'll say, okay, I'm going to look forward just a little bit. I'm going to look at your flink. And I'm going to assign that the value of list head. Okay, list head being the very beginning. And then I'm going to go to your backwards pointer, your blink. Okay, and that blink is going to be this blink variable here, list head blink. Okay, we're doing this to maintain that circle, right? The circle of life. And then our blink flink, this is getting crazy, I know. Blink flink equals entry. Okay, meaning we're now adding this one, we're updating on the linked list, all those entries of flinks and blinks properly to go ahead and link everything together. List head blink. Okay, so looking at the list head, going backwards, entry. Okay, whatever this current entry item is, okay, that is now going to complete the circle of life. Let's see if I can draw this out real quick. All right, so, that's not the right one. All right, so that is the list head, and this will be the first item. Okay, now, as of this moment in time, your flink and blink, I can get right here. That's a terrible straight line. Okay, so this is the head list. It has a flink item, right? Just say flink and blank. That's it. And they point to each other, right? That's it. They're out there in no man's land, and they're pointing to each other wherever this happens to be executed using heap, not executed, allocated using heap alloc. Okay, it's pointing to that chunk of memory. Boom. But we're adding something. We're adding something to it. All right. So we have another item that has a list entry structure, and it has a flink and a blink. Okay. So what's going to happen here is we're going to come into, excuse me, we're going to come in here and update these pointers. Okay, so let's try and walk through this with code 2. Blink. All right, this is our temporary placeholder, just being updated to list head blink. Now let's look at this entry. Entry flink. Okay, so let me type in F B. So entry flink. That's what this is right here. Entry flink is going to point to the list head. Boom. Okay. List head. Entry blink is going to be pointed to this guy right here, this blink, which is list head blink. Okay. This is nuts. I know. All right. I wish I could draw like circles around this. Okay. Then it's going to look at the blink flink. These names are crazy. The blink flink is going to point to entry. Okay. So blink again is looking at list head blink. So that's this guy right here. Okay. And that points to entry. Weird. Okay. And then, and then the list head right here. Yeah. List head blink is pointing to the entry. Okay. All right. So crazy way of trying to visualize how we add something to the head of a list using all these pointers. This is madness. Okay. Again, this is something that's not very easy to pick up straight away, right? Even trying to draw it out, right, with all these arrows can get very complicated very quickly. Can we change the name of the variables? Yes, you can change the name of variables as you see fit change it to whatever makes more sense for you. Absolutely. Change away. Okay. Let me go ahead and get rid of that. Okay. Get rid of that drawing. And what we do here in code, I know we're getting pretty close to the end here. Let's go ahead and allocate a chunk of memory for our procinfo structure here. Procinfo equals p process info x and heap alloc. So I'm just going to copy and paste the heap alloc. Of course, I'll have to change one argument for that. So it can't be size of list entry. It has to be the size of our structure. Again, it's not a pointer to this structure. It is the actual structure itself, process info x, not p process info x. All right. So if this fails, let's error check. Then we update the variable to say if not procinfo. It's fail and bail. And now we can fill out some of the structure items here. Procinfo. And since we have a pointer to this, we use what's called arrow notation instead of dot notation. And current thread. Let's initialize the current thread and the name just real quick. Get current thread. Oop, if I can type. Get current thread. Don't give it any parameters because it doesn't need any. And p procinfo. Name equals, and I need to make one. So let's do Unicode string. US proc name. Okay, so again, we'll use our RTL constant macro to go ahead and initialize this one. Okay, so RTL constant string. Constant string, and we'll say this is explore. Okay, explore.exe and US proc name. Cool. So we just initialize 2 items for this whole entry. Okay. Now what I want to do is insert tail list. And what we need for this to work is a pointer to the head of the list. So that's going to be temp head list and the current entry. Okay. Now, this is where it can get a little bit interesting. All right. So pprocinfo, arrow notation, process info links. We need the address of that. Okay. This is of type list entry. You cannot insert tail list or add to the tail list of any other structure member type. It has to be of type list entry because they all point to list entry types. Okay. So go ahead, and one last thing I want to add, copy and paste this to do a test to see if the list is still empty or not. Okay. So we have insert tail list, adding that item to the right after the list head and seeing if it's empty or not. Okay, let's update the breakpoint to go down there. And let's go and fire away. All right, watch window. Cool. Indeed. All right. So all we did here in the last minute of time here is you can see how the Flink has now been updated to the newest entry that we just added to our list, okay, which is pproc info. Okay. I know that's a ton of stuff to cover, in just a short amount of time. And I think what we need to do to properly end this is in part 5, pick up right here where we're leaving off in part 4 to dive down even further into these doubly linked lists. Okay. That way we can spend just a little bit more time. Okay. So I know it is actually at the top of the hour. We are officially at the 2-hour stretch here. So I will go ahead and sign off. If you want to carry the conversation over in Discord, Sans Workshop, please feel free. I also created a separate Discord server more specific for the course where we can carry conversations there as well. Thank you so much for tuning in. I really appreciate your time over this past 2 hours, and hopefully you learned something about structures, linked lists, and creating some functions that take in pointers to these types as well. Thanks so much, everybody. Catch you next month for part 5.